Hello everyone. In today's video, we are going to continue talking about conservative forces. It's like the continuation of our last video. We are going to treat the third and the fourth point we were looking at the previous day, this and this, because in the previous video we were looking at the two first points, and now we are going to look at the third and the fourth point. So, just to make a recap from the last video, if you have a random vector field, in this case the vector field is a force, if you have a random or a general distribution of forces, what I did in the previous video was decomposing this general force distribution into two different case scenarios. In this case scenario, in which each component for the force depended on the rest of the components for the position, or vary with respect to the position at the other component and the rest of the components. And in the second case scenario, the component of the force varies only when we make a variation in that same component for the position. I mean, the x component of the force varies when we make a change in the x component of the position. And exactly the same thing happened here with the y component. The reason I'm doing this is because we are going to analyze each case separately, and we are going to get to the conclusion that the first case scenario is the only thing that is the only case scenario which we have to take into account to determine if a force is a conservative force or not. The second case scenario we'll see now in the demonstration, or in the procedure we are going to apply in a moment, that the second case scenario doesn't have any influence, only the first one. That is the reason why I split it into these two cases scenario, because we are going to analyze each one separately and we'll realize that the second one doesn't have any influence. So let's start with the point 3. I mean, the analysis of the first case scenario. If you take a point here, you take a region around that point, very tiny region around that point, you will see, I explained before in the previous video, that the variation of the x component with respect to the position in y, and the y component of the force with respect to the x position is almost linear when we take a very small region around the point, okay? So if you have a point A here, which is the starting point, and a point B, which is like the end point, okay? Remember that these 2 points are within this tiny region, which means that these 2 points are very, very close to each other, infinitely close. However, if you want to move from point A to point B, what we are going to do is to take 2 different possibilities, 2 different trajectories. A trajectory A, which goes from A to B like this, and a trajectory B, which goes from A to B like this. So if you notice, both trajectories, or trajectory A and trajectory B, they are inverses trajectories each other. So first we move in X and then we move in Y for A, and for B, from B, first we move in the Y direction and then in the X direction. If the field is conservative, the work we do, if we move like this or if we move following B, must be the same. This means that the work at A, the work done by following path A, is the force that we initially have, because F sub A is the force at A, at the initial point, which has 2 components, the x component of the force at A and the y component of the force at A. The work done by that force is going to be that force, I mean, the x component of that force times the x. This work you see here is the work from moving from that point A to this point, that intermediate point between A and B following path A. Plus this force times dy. Remember that when we move this amount, this horizontal length, there's no, the y component of the force doesn't make any work. At this segment, the only force that is making some work is the x component of the force, but not the y. And as we are moving to the right, some new forces appears, but that new force is not a force in the x-axis, but a force in the y-axis. And that is the reason why here, in this second term for the force that is actually making the work for moving from that point to B is that force. Because at that point, the total force is going to be the initial force, the initial y component of the force, plus the new force that appears due to the fact that we are moving throughout this axis, the horizontal direction, to the right. What is that differential, or that infinitesimal increment of the y component of the force? Is given by this. This is the derivative of the y component of the force with respect to the x component at A, when we are very close from A, very close to A. This derivative at the, at the areas or at the zones that are very close to that point A is almost constant. Because remember, the evolution of f of x and the f of y is almost linear when we take very small radians. And that is the reason why this derivative is almost linear. So this derivative times dx, which is the amount of x we move to the right, will give us the increment, the infinitesimal increment of the y component. And that total force, the initial force plus that increment, times the distance, this distance in the y direction, which is dy, will give us the work done by following this vertical segment. And that is the total work done by following the path A. If we follow instead the path B, the procedure is really similar. However, here we have that in the first part of the path, the work that the force that is making some work is the vertical force. And in the second part, the only force that is making some work is the x component. And in the x component, we have some increment, which is developed like this, in this way. Very similar. It's the same than in the previous case, okay? So, if we consider that both work has to be the same, it's necessary that the two works have the same value, because if not, the force field wouldn't be conservative. In that case, we have to make them equal. We have to force them to be equal. This is the work A and this is the work B. If you develop this a little bit, you will end up with that expression here. This. This is the condition that must be met in order for a force to be conservative around the point we are studying, which is the point A, the starting point. So if you take a very small region around that starting point, point A, and that condition is met, this means that at the surroundings and the areas that are very close from that point A, the field or the force field is conservative, at least in the regions that are very close to that location. However, how can we ensure that the force is fully conservative? In order to ensure that the force is fully conservative, we need that condition to be met not only at point A, but at every point, at all of the infinite points that we have in the space. If that condition is met for every point, that means that the field is conservative, the force field is conservative. If you see those formulas, those equations, you may realize where they come from. If you have ever seen something about conservative force at uni, these formulas may sound familiar to you. And they are exactly the same formulas that we have seen up here at the initial, belonging of the first video, the last video. And that is a reasoning of why this formula, or where that formula comes from. And what about the second case scenario? I mean, this case scenario here. Well, in this case scenario, it is not necessary to take very small regions around some specific point. We can look at this more from a more macroscopic point of view, from a bigger scale. In that case, we have variation. In the second case scenario, we have variation of f of x with respect to the x position and f of y with respect to the y position. What does it mean? It means that if you are moving in the x-axis through the x-axis or the x direction, there's no variation in the y component, only in the x component of the force. The same applies if you are moving in the y-axis or in the y direction. There's only variation in the y component of the force, but not in the x component. What does it mean, all this that I'm telling you? This means that the force distribution here at this segment is exactly the same than the force distribution at the upper segment. And the same than at this segment, and this, and this, and this, etc. And exactly the same thing applies to the vertical. The vertical component of force, that distribution is exactly the same here than if you take this, or this, or this, or this another segment. The forces distribution are going to be exactly the same, because there are not crosses relationship. There are not, cross relationship between the force and the position. I mean, the x component of the force does not depend on any other component of the position, only on the same component for the position. And the y for the force depends only on the y for the position, and so on. What does it mean? It means that if the force distribution is the same, this segment is going to make, by following this segment, we are going to make exactly the same amount of work than this segment, than this segment, than this another segment. And this vertical segment is going to make exactly the same amount of work than this one, this, or this one. This fact leads us to get to the conclusion that this second case scenario, as I told you before, doesn't have any influence when determining if a force field is conservative or not. So that is a bit more about the idea, theoretical idea or understanding behind this topic. I hope you understood, or you have a bit more clear about the understanding of this topic, because it's something that it's not easy to find an explanation of that. So I hope it is helpful for you. If so, I'm very happy, and see you in the next video then. Bye.